class. So today we will dive straight into the notion of compact space. So we are going to tackle the notion of compactness. So without any further ado, I'm going to share the screen with you. So we are going to talk about compact topological spaces and compact sets. So by definition, if X is a topological space, a subset K of X is a compact set if, first of all, it's non-empty set, if K is a non-empty set, and beside, if for any covering of K by open sets, we can extract a finite subcovering. So what does that mean? It means that if we have an arbitrary covering of K, let's say this is K, let's say this is K. If you recall with the sub-intervals of the intervals of R, when we tackle exterior measure or outer measures, you recall that we took an arbitrary, when we defined the exterior or outer measure of a subset, an arbitrary subset of R, which is not necessarily an interval, right? A is just an arbitrary subset. It can be anything, provided it's a subset. We saw that this A, we can cover A using open interval. Right, arbitrary. Yeah? I is in the set of indices. So such a covering, now we are in a space which is not necessarily R. It's anything. It's a topological space. Now, if this is our K, we assume that K can be covered by open intervals of that topological space. So in this particular case, you can have something like this. You have a covering. That is when you take the entire union, this entire union, right? All K is contained. It can be an infinite, arbitrary whatsoever. So from this covering, we can find a finite number of them that still covers K. That's exactly what it means for a subset of a topological space to be a compact set. Okay. Okay, now from the definition of a compact set, we can define now what is a compact topological space. Now, a topological space Xt is said to be compact if every open covering of X has a finite subcovering. So it's the same. Here now we replace K with X. And now for X, we will no longer say that X is contained, right? Because we know that all that union will be contained in X. Now we say X equal to, right? So for a topological space, instead of inclusion, we just say for any covering, now X is the union, like that. So now if you can find a finite such that is still covered, that is, if you can find a finite like this, such that K is still the union now, IK, where K is run from 1 to n, that is a finite subcovering of the same X, then we say that it is compact. So this is an arbitrary, because for every, so this is an arbitrary open covering. So if from that arbitrary we can find a finite number of those open sets which still covers X, then we say X is a compact set. So that is exactly what we have in this case. Now we are going to give you some example of compact sets and compact okay, so if you let our capital X to be R, end up with the usual topology, any closed and bounded sets of Rn is compact, but Rn itself is not compact, meaning that when n is equal to 1, R is not a compact set, right? Okay, so we have this fact that any closed and bounded set of, okay, now in the case of R, if you take any closed interval of this form AB, this is a compact. It's compact. For any A and B, where A is less than B. So this is a compact because you can see that it is closed and it's bounded because you can always include this in a single ball or a single interval. You just take if you take the when you say bounded, it means that it can be contained into something. So if you take this, you can contain it in this. You just take A plus epsilon, A minus epsilon here, and A plus epsilon will be contained there, right? All right. But we'll come back to this, right? We'll come back to that. For now, let us go into the understanding of all this means. All right. Now, this interval open at A at 0 and close at 1, you see that it is not closed. So it doesn't fall into this category of closed and bounded. It's bounded, but it's not closed, right? Because it's open at 0. This is not compact. Obviously, we can prove it right away. K, this K is contained in the union. You can see if you write this, take each open set to be 1 by I and open at 2. So all the points here will be in the union of that. When you take union on a countable union, where I is element of n, that is natural integer. Now you can prove this. You can prove this. It's easy to prove, right? So this is true, right? But this, you cannot extract from this. You cannot find a finite number that will still contain. You cannot. It's easy. You can just assume that that is possible, right? If you assume that is possible, you will reach to a conclusion. I mean, to a contradiction. If you assume that you can find a finite number such that this is still there, you reach a contradiction. right? Okay, contradiction, what does that mean? Okay, now if you assume that K can be covered by a finite number, meaning that K is contained in the union I running maybe from okay, like this. Okay, let's use this one. This one, a finite number like this. But in R, don't forget that these are intervals. They're intervals. So meaning that you can have a finite number of intervals like that will contain this. Now, if you take an element of K, which is, for instance, this is K, right? You are here. This is our K. The contradiction will not come on this side because there's no problem with the right part of the interval endpoint, but it will come here with the OIs. Because this union is finite, right? You can take the largest one. That is because you have a finite number. So if you take the largest I or the smallest, because if you take the smallest I, it will give you the largest. That is on the right, you take the largest, right? The largest would be the one with the smallest I. If you take that one, you can show that there will be a contradiction. How do you show that? So if you look at this one, you can see this interval is open at 0, right? So you take anything that is less than 0 but not 0, which is an element of K. But you can show that one of these elements cannot be covered by the largest, or yeah, the largest. Huh? When I say largest, that would be the smallest one by I. Okay, so let's say, because when we will take all this union, the finite union, up to this n, right? So if we assume that this n gives us the largest, when I say the largest, it means that we have something like this. Let's say IY. I sub k, let's say k0 like this, and this is 2, because they are all of that form, right? This will be the largest subinterval of that form. The other ones, that is this one. Now, if I take an element here, an x here, if I take an x that is positive, like this, that is close to 0. We take an x that is very close to 0. What do we realize? So we can realize that for this, well, this is a rational number, this one, which is the largest, right? This is a rational number. So this belongs to Q. It's a rational number. 1 by I sub Q0 is a rational number. But this x, which is greater than 0, we can select this x greater than 0, also less than 1 by That is possible. So we see already that this x will not be in any of these finite terms. We can always find it. We can always find it, always. So this is what the contradiction will be. So that's why here we say that it is not enough. This interval, I mean, we cannot find, but a final number of those open intervals is not enough. So if you take a final number, it will not be enough to cover k, because here we have x, which is an element of k. You can see this x is an element of k. So here we can say let x be an element of k such that x is less. What did I write here? Yeah, less. Yeah, x less than that by this 1 by ik0. Where 1 by ki0 is the largest such interval that contains k. So we can always find it. We can always find that. So it means that we can really find such an element of k that will not be covered by this final number. It's always possible. And why is it possible? It is possible because Q is dense, right? It's dense in R. We just use that fact. We use that density. So we can always find an element of k that is not contained in any of these. And this is an example. So for that to be true, we need that interval to be closed. If it is closed at at 0, then it will be compact. But if it's open, it's impossible. By density of Q in R, we can always prove our point. Okay, so similarly here, this number 3, k, close at 0, open at infinity, is not compact for a similar reason. As in 2, not 1. This should be 2. And this is 4. Okay, now this one is compact. We close interval 0, 1. So 0 and 1 can be replaced by AB. This is just a particular case. But as I mentioned here, any closed interval AB is compact. So this is compact. I will not do that today. I encourage you to do it, but I will record another video where I will do the proof for this one, for you to see the procedure. The purpose of this one, of this class, it will not be long. It's just to push you to read and try to do the problems. I posted tutorial 2, and now by Friday, I'll also release assignment 1, and you will have about 1 week and a half to submit it. And I'm also intending you to write a test by the end of next week. It will just be test 1. It will be simple, just for you to first have your first test. At least it will show that our class is active, right? So by the end of next week, you write the first test. But during the course of this week, so that is by Saturday, I will try to record more videos, and we'll also have tutorials to prepare you also to write the test. Okay. So as I said, the proof of this one, compact, we will do that maybe by tomorrow in one of the videos that I will record. Okay, and another definition. A set A, let A be a non-empty set a collection of subset of A is said to have the finite intersection property, if every finite intersection is non-empty. So every finite intersection is non-empty. That's what we call finite intersection property. Finite intersection property means that any finite intersection of the set A is non-empty. Right. Of course, if any finite intersection of that collection, right? Because what in fact is this collection that has the property, not A itself. Right? It's not A itself, but we say a collection is said to have. So it is the collection that has the finite intersection property, not A itself. It's the collection. So if I have a set, a non-empty set from a topological space, of course. Obviously, here we did not mention that we are dealing with the topological space, but don't forget that this subsection is about topological spaces. So we have a non-empty set A, and then we take a collection of subset of that A. Now, that collection will be said to have the finite intersection property if any finite intersection from that particular family, from that particular collection is non-empty, meaning, because we say any, if every finite intersection, meaning that if you take two arbitrary, just two, the intersection should be non-empty. If it is, if two arbitrary subset of the collection are disjoint, therefore there's no longer we can no longer talk about the finite intersection, because we say any or every finite intersection, two is finite. To talk about non-empty intersection, you need at least two before you can go to more relevant. Okay, so that is about the finite intersection property for a collection. Now let us use that definition of a collection having the finite intersection property to characterize a compact topological space. Right. So that's the purpose of the following theorem. A topological space Xt is compact if and only if and only if every family of closed subset of we are now here. So this capital X is like our A. Every family, that family is our, like this collection. So this family, every family, we can replace this every family with our collection A alpha. Right? And now the element of the family are closed. So A alpha closed. So if and only if every family of closed subset having the finite intersection property has a non-empty intersection. So they say if and only for every, so that in that topological space you take an arbitrary family of closed subset having that property. Now, if you find such a family, no, not that if you find any arbitrary. So if you have such an arbitrary, then you take the intersection of all the elements now Remember that when we talk about finite intersection property, we only take the intersection of a finite number of them. But now here you are told that if you have, if your space is a topological, if your topological space is compact, now every family or collection having this property, right? Having this property, because that collection is an arbitrary collection from which you select a finite number, and you find that that is finite intersection is non-empty. But now, the family itself, if you take the intersection of all, so now instead of finite, now you take the entire intersection like this. This should be non-empty. It's no longer finite. You don't select a finite among the AKs, finite like this. But now you take the entire, because if you take a finite among this A alpha, because it has that property, right? The collection has the property. Then it will be non-empty. But now you don't take a finite, but you take all of them, the entire. If you take the entire, it should be non-empty. So this is a characterization of compact set. Okay, now the second one is every closed subset F of a compact topological space is itself compact. Of course, when we say it's itself compact, it means it is compact for what? For the induced topology, right? Every closed subset F of a compact topological space is itself compact. So let's say that this is a topological space and X is compact, right? X compact. And then we have F, a subset of X, which is closed. If F is closed, that implies that F is also compact. So that's the theorem. If I have a topological space, and then from that topological space I take a closed set, that closed set is compact. So the characterization of, not characterization per se, but any closed subset of a compact set is also compact. So X is a compact set. If you are asked to prove that a subset or a subset of a topological space of a compact topological space is compact, just show that it's closed. You don't need to show anything else. Just show that that subset is closed. Full stop. Why? Because after the theorem, if it is closed, it's compact. Okay, so that's a way to exploit that result. But in R, you cannot say that, okay, if I have a closed set in R is compact. No, that's wrong. Why? Because R is not compact. And you can prove from this, after doing this, you'll be able to show that R is not compact. You just take an arbitrary, you show that, you take an arbitrary covering of R by open set. You show that a finite number is not enough. So you take a finite number and you do exactly what I did here to show that that will not be possible. For R, it's even very easy, because for R, if you take a finite, you take the largest. If you take you can always construct. You can always write R as the union of open interval, or contained in the union of open interval. Now, if you take a finite number of them, because R, is an interval, it goes to infinity. Now, if you take a finite number of covering of R by open set, In fact, when I say if you take, since it doesn't exist, but if you assume that such finite covering exists, you just use the largest interval. So you go to the largest interval to the right or to the left, depending, but I will take to the right. You take the largest value. If you fix that interval, because R goes to infinity, that number that will be there, you will always take that final number, you add 1, you are out of that range. So you show that it's not possible to cover using a finite number. So it doesn't work. Okay, next thing. Every closed subset of a compact Hausdorff space is itself a compact Hausdorff space. So that's a corollary of this theorem. Other theorem, I will not go through all these theorems because there are many. I will not cover all of them. Please, I encourage you to read. I'll go straight to the part that is important, right? For now. Okay, so let's look at this theorem. Continuous mapping and compact sets. Is this a good result, an interesting result that is worth mentioning? So we have a topological space X, T sub X, a compact space, and F, a continuous mapping from XTX to another topological space, Y, T, Y. Then F of X, that is the image of our compact set by a continuous mapping. So if you take such an image, we're told that if you indulge the image with the induced topology, because F of this is a subset of Y. Y is a topological space, right? The only thing that is compact here is X. We don't know if Y is compact or not, so there's no such information. So we assume we take the largest property that we can have. We assume it's not compact, right? It can be, but it might not also be compact. So we assume it's arbitrary, so it's not necessarily compact. So now we are told that if we take such an image and then we take the induced topology, that is the image intersection to the topology of Y, it becomes compact, right? So in other words, what can we say? What can we say? In other words, we can say that if I have a function that is continuous from a topological space to another one, if the initial, I mean, when I say initial, if the first space, which is like the range, is compact, then the image of the compact is also compact there. That is when we take it as the induced topology, right? The induced topology in the target space, which is Y. So if you take the induced topology, that one will be compact. And this is the proof. You can read it yourself. We might come back to this in application or in tutorial. But what I want to dive into now is the matrix space. Because this rest, you can read it yourself, right? But what I want to dive before we part today, I want us to define what is a matrix space. Because that's something that is due. We really need to define what is a matrix space. And from the matrix space, there are many other things that you'll be able to do, because everything is based on the definition of matrix space. When you come to Banach space, the LP spaces and everything, they are all what we call a matrix space. Now we need to tackle that definition. When you say matrix space, it means that it's a space with a matrix, something that allows us to take the distance. Because when you say we have a meter, because you want to measure distances, right? If you have 2 points, how do I measure the distance from A to B? So if in a space, I have an instrument that allows me to measure, right? An instrument that allows me to measure the distance between 2 arbitrary points, I say that that space is a matrix space. Now, I need to define in an arbitrary space or set what is the distance. So we need to define what is the distance. Once you have the distance, the definition of a distance, you can define what is a metric space. So first thing, so we have a non-empty set. E is not a topological space. Yes, nothing. You don't have the notion of topology at this level. It's just a non-empty set. E. Now on E, we can define a distance, right? A distance is what? It's a function of two variables, x and y, because when I measure the distance between 2 points, so I define a function from the Cartesian product of E by E into R that satisfies these 4 axioms of properties. So any function of two variables that satisfy these 4 properties is called a distance. The first is that the distance between 2 points is 0 or positive. The second property is that if the distance between 2 arbitrary points is 0, it means that the 2 points are the same. The 2 points coincide. Because if they are distinct, the distance cannot be 0. But if they are 0, it means that it's the same point. That's exactly what this means. Distance from x to y is 0 if and only if x and y coincide. It's the same point. The third property is the symmetry, meaning that the distance from A to B is the same as the distance from B to A. So no matter the direction that I take, between 2 points, the distance is the same. And the last property is what we call the triangle inequality or triangular inequality. It is something of this form. If I want to measure the distance or I want to compare the distance from A to B, this is A, and this is B, right? If there is a supplementary or another point somewhere there, this distance will always, this distance from A to B, this distance from A so this distance will always be less than or equal to the distance if I first pass through an intermediate, not necessarily on the path, but a point that is not there from here to there. So if instead of going straight from A to B, I decide to go through another point which is not along the path, right? Then it will be less. This distance will be less than the distance. Okay, let me call this 1. Okay. This is A, this is B, this is C. So this is 1. Let's call this 1. Let's call this 2, and this is 3. So if I take path 3 directly from A to B, fine. But if I pass through A and 1 and 2, you see, I'm using a longer trajectory. The trajectory will be longer, meaning that the distance from A to B will be less than or equal to the distance from A to C, and then the distance from C to B. So this one will be less than that one. Obviously, there can be equality if C is along the path. So that is if it's in between the 2 points, right? That is, if I join A and B by a straight line and C is on that line, then the U will be equal, right? Okay, so that's what we call the triangle inequality. Okay, now the definition of a metric space. Now that I know what is a distance, what is a metric space? Of course, before we give you example of distances. Now, if on E I define a distance, like we did here, if this D is a distance defined on E, the couple or the pair ED is what we call the metric space. That is the space in which we take D to be our distance. This will allow us to measure the distance between 2 points. Now, this pair is what we call metric space. Metric space. So the definition of a metric space is really simple. It has nothing to do with topology, no. Just empty set, you define a distance. Now it becomes a metric space. Now the good news is that from this metric space, we can define a topology on E. From a metric, I can always define a topology, and we'll see how that's possible. But metric space has nothing to do with topology. Of course, in the first side, we'll see later on the connection, right? Okay. Now, here you have examples of distances. There are so many. I will not go currently into, for the sake of time, since I say that for now, I will not spend too much time. I wanted us to tackle that notion first. But let us look at the first example, just one. Okay, maybe you have already seen something before, otherwise maybe this will be your first time. If we take our E, right, to do this is E equal to, we take the set of continuous function or the closed interval 0, 1. So if E is that, because this is a non-empty set, you can always define a continuous function in the interval 0, 1. So it's non-empty. So that's our E. Now over this E, you see that we say distance is for two, need a pair, Fj. Now the distance from F to J is defined as the maximum of the absolute value of the difference F of X, G of X, where X is an element of the closed interval 0, 1. This max exists, right? It always exists, this max. Because the function is continuous, the max will exist over the closed interval. So this is a distance on E. And how do you prove that it's a distance? You just show that axiom 1, 2, 3, 4, all these three are satisfied with this definition. So for the first one, you can read it by yourself. The second one, you see the proof. The third one, this is the proof. And finally, the triangle or the triangular inequality is given by this. So please read that. You are mature, you can read. But if need be, we might have a tutorial where I will go through, but you can read that on your own. If you have problems of understanding, you can always ask and we'll cover that together. My purpose is to push you to read, to understand the concept, because the purpose of giving the notes to you in advance is so that you feel free to read, to be proactive in your reading, to try to understand that this is about metric space, but what does that mean? That curiosity, because we will not chew or go everything line by line. At this level, you are mature, you can read on your own. So that's why I'm trying to do with you, because they are concepts, because it's a vast concept, the concept of metric space. And if you have to go through each detail, we will not cover the program, right? So that's why I encourage you to read, so that when we meet, you can address the problem straight away. All right. Okay, I already defined what is a distance, what is a metric space, even though it will be defined later on. But that is it. Now, this concept of underlying topology to a metric space, because remember I told you that if I have a metric, I can define a topology. And that is what this part is all about. We'll do that next time. I will not tackle that for now. I encourage you to read and be able to redo this example yourself without looking. Read first, try to do it by looking, but you should be able to do that on your own so that it becomes like a reflex, so that if something new is defined to you, at least you have an idea from what it's known. Okay, so I hope you will enjoy the class. If there's something you don't understand, please let me know so that we organize a session and discuss about it. I will stop here for today, and thank you so much for your patience. God bless you and see you next time. Bye-bye.